Hello students, in this video we are going to see solution for previous year NEET question paper. Particularly we are going to focus on the topic called kinetic theory of gases. Before going inside the questions, let us have some statistical analysis about the previous year questions, like how in what are all the topics major questions were coming. So if you see the kinetic theory of gases unit, we have total 5 subdivisions. The first one is kinetic of an ideal gas laws. Second one is speed, pressure, and kinetic energy of gases. Third, degrees of freedom. And fourth one is specific heat capacities of gases. And fifth one is mean free path. So out of all these 5 subdivisions, if you see the first one, the kinetic theory of ideal gas and gas laws, about 15% were questions were coming from that, and about 32% of questions were coming from speed, pressure, and kinetic energy of gases, and 12% from degrees of freedom, and 33% from specific heat capacities of gases, and 8% from mean free path. So this was the strand for the past 33 years. Now if you see for the past 8 years, about 20% of questions were coming from kinetic theory of an ideal gas and gas laws, and 25% from speed, pressure, and kinetic energy of gases, 10% from degrees of freedom, and 30% from specific heat capacities of gases, and 15% from mean free path. So if you just have a look at the previous one, for the past 33 years, majority of the questions were coming from specific capacity of gases and speed, pressure, and kinetic energy of gases. In a similar way, for the past 5 years also, if you see the trend, majority of questions were coming from specific heat capacity of gases and speed, pressure, kinetic energy of gases. So in this video, we will try to solve sample problems for all the 5 subdivisions, and importance has been given to these two specific subdivisions: speed, pressure, and kinetic energy of gases, and specific heat capacity of gases. Okay, so let us move on to the first question. A cylinder contains hydrogen gas at pressure of 249 kilopascal and temperature 27 degrees Celsius. Its density is, so they are saying like a cylinder which is containing hydrogen gas at a pressure of 249 kilopascal and temperature is around 27 degrees Celsius. What is its density? They are given the R value as 8.3 joule mole inverse Kelvin inverse. So the molecular mass of hydrogen is so molecular mass of hydrogen M is 2 into 10 power minus 3 kilogram, and density is given by density is equal to M by RT. Okay, so here the pressure is 249 Kelvin Pascal, sorry, 249 into 10 power 3 because of the kilo, and into the mass is 2 into 10 power minus 3 divided by R is 8.3 into temperature, you are changing it into Kelvin, 27 plus 273. So if you are trying to solve this, you will be getting the answer in the range of 0.2 kilogram per meter cube. So the correct answer is option number 1. So it is a very simple question, mere substitution of the formula. Here they are telling that a cylinder is containing a hydrogen gas at a pressure of 249 kilopascal and temperature 27 degrees Celsius. What its density is, and they are given the R value. So here they are giving you the R value, they are giving you the T value, and the P value. The M value we already know. Molecular mass of M hydrogen is M is equal to 2 into 10 power minus 3. So you are going to substitute all these values, and when you try to solve it, you will be getting the answer as 0.2 kilogram per meter cube. Okay, so the next question is, a given sample of an ideal gas occupies a volume V at a pressure P and absolute temperature T. The mass of each molecule of the gas is m. Which of the following gives the density of the gas? So we all know that the ideal gas equation is given by PV is equal to nRT. So for n is equal to 1, V will become RT by P. Okay, so density is given by density is equal to molar mass by volume. So it is m into Na into P by RT. But R by Na is equal to Boltzmann's constant. R by Na is equal to Boltzmann's constant. So density will become mp by kT. So the equation for density is mp by kT. So the correct answer is option number 3. Okay, so you're making use of the ideal gas equation P equal to nRT, and you're taking n is equal to 1 and you are calculating the formula. Density is equal to molar mass by volume, and R by Na is Boltzmann constant. You are going to substitute, so you'll be getting the final answer as density is equal to mp by kT. Okay, so let us move on to the next question. The average thermal energy for monoatomic gas is, so they want us to find out the equation for the average thermal energy of a monoatomic gas, where Kb is the Boltzmann constant and T is the absolute temperature. So according to the law of equipartition of energy, the energy per degree of freedom is 1 by 2 kBT. So the energy per degree of freedom is 1 by 2 kBT. So this is based on the law of equipartition of energy. So monoatomic gases will be having 3 degrees of freedom. So monoatomic gases will be having 3 degrees freedom. So therefore the average thermal energy will become 3 by 2 kBT. Okay, so the correct answer is option number 1. So based on the law of equipartition of energy, the energy per degree of freedom is 1 by 2 kBT, where kB is the Boltzmann constant and T is the absolute temperature. In the case of monoatomic gases, it will be having 3 degrees of freedom. So the average thermal energy will become 3 by 2 kBT. So the correct answer is option number 1. Okay, so let us move on to the next question. At what temperature will the RMS speed of oxygen molecules becomes just sufficient for escaping from the Earth's atmosphere? Given mass of oxygen molecule m is equal to 2.76 into 10 power minus 26 kilogram, Boltzmann constant Kb is equal to 1.38 into 10 power minus 23. So they want us to calculate the temperature at which the RMS speed of oxygen molecules becomes just sufficient for escaping from the Earth's atmosphere. So the escape velocity at the surface of Earth is given by escape velocity escape velocity at is 11.2 kilometer per second, or it is 0.2 into 10 power 3 meter per second. So oxygen will escape when RMS speed of its molecules uh, is equal to the velocity. So C RMS is 11.2 into 10 power 3 meter per second, or it is square root of 3 kBT by MO is equal to 11.2 into 10 power 3. So CRMS is root of 3 kBT by M naught, or you take the square of this, it will become 3 kBT by M naught, taking the square root on that side. So this will become 11.2 the whole square into 10 power 6, or T is equal to 11.2 10 power 6 into M naught is 2.76 and 10 power minus 26 divided by 3 into 10 power minus 23. Okay, so when you solve this, you will be getting the answer in the range of 8.36 into 10 power 4 Kelvin. So this is the correct answer. So the right answer is option number 2, 8.360 into 10 power 4 Kelvin. So here they are telling us to find out the temperature at which the RMS speed of oxygen molecules becomes sufficient for escaping from the Earth's atmosphere. So the escape velocity of Earth's atmosphere is 11.2 kilometer per second, and they want to know the temperature at which the escape velocity is equal to the RMS speed. So CRMS will become equivalent to 11.2 into 10 power 3, and the formula for CRMS is root of 3 kBT by M naught. So you are substituting, and all these values they have given. Okay, so they given you the kb value, they given you the M naught value. You're going to substitute, and the final answer is the temperature is 8.36 into 10 power 4 Kelvin. Okay, so let us move on to the next question. The molecules of a given mass of a gas have RMS velocity of 200 meter per second at 27 degrees Celsius and 1 into 10 power 5 Newton per meter square pressure. When the temperature and pressure of the gas are respectively 127 degrees Celsius and 0.005 into 10 power 5 Newton per meter square, the RMS velocity of its molecule in meter per second. So first initially they given the molecules of a given mass of gas which is having a RMS velocity of 200 meter per second. So that is the first one, the C1 value, and so the C1 value is 200 meter per second, and they have given the temperature as 27 degrees Celsius T1 and P1 as 1 into 10 power 5 Newton per meter square. Now they have given when the temperature becomes T2 is 127 degrees Celsius and P2 is 0.05 10 power 5 Newton per meter square. They're telling us to calculate what is the C2 values. Okay, so we all know that CRMS is equal to root of 3 RT by M, or you can say that CRMS is directly proportional to square root of T, or you can take it as C2 by C1 is equal to square root of T2 by T1. C2 is equal to C1 into square root of T2 by T1. So C2 is equal to C1 value is they are given as 200 square root of 127 divided by 27 plus 273. Okay, why we are adding this 273 is we are converting it into Kelvin. So 200 square root of 400 by 300. So when you are trying to solve this, so you will be getting the answer as 400 by root 3. So if we solve this, you will be getting it as 400 by root 3. Okay, sorry, this is root 3. So the correct answer is option number 4. So it is a very simple problem. You are going to make use of the equation called CRMS equal to root of 3RT by M, or CRMS is directly proportional to root T. So here they have given two conditions. First condition, the temperature is around 27 degrees Celsius, and in second condition the temperature is around 127 degrees Celsius. And in the first condition they given you what is the CRMS value, RMS velocity. Next they want us to calculate what is the RMS velocity at this particular temperature. So you are going to just substitute the values and you are going to easily find out. So the correct answer is option number 4, 400 by root 3. Okay, so let us move on to the next question. Two vessels separately contain two ideal gases A and B at the same temperature. The pressure of A being twice that of B, under such conditions, the density of A is found to be 1.5 times the density of B. The ratio of molecular weight of A and B is. So here pressure exerted by the gas P is equal to but C is equal to root of 3 RT by M, where M is the molecular weight. So P will become automatically 1 by 3 into 3 RT by M. 3 and 3 will get cancelled. So you'll be getting the molecular weight M is equal to rho RT by P. So here we have got an equation for the molecular weight. What they are asking is they are telling us to find out the ratio of molecular weights of A and B. So in respective to the density. So molecular, since M is directly proportional to rho, here you can take this as MA by MB, MA by MB will become rho A by rho B, since rho is directly proportional to M, and then TA TB, since temperature is also directly proportional, but PB by PA, because the pressure is inversely proportional to that. So here the density ratio is found to be 1.5. So this will become 1.5. This will become 1.5 into the ratio of mole. That's what they want us to find, and the temperature is same. Okay, so the temperature is same, so it will be 1 into the pressure of A being twice that of B. So this will become 1 by 2. Okay, so this they have given in the question itself. Uh, the density they have told it is 1.5, so we are writing it as 1.5, and here the temperature is same, so you are putting it as 1, and the pressure is twice. So since it is inverse, rho is at the bottom, you are making it as 1 by 2. So if you solve this, you will be getting the answer as MA by MB is equal to 3 by 4. So the correct answer is option number 3. So it is also a simple problem only. Just you are finding out an equation for the molecular weight, and you are taking the ratio of the two ideal gases A and B, MA by MB, and we are finding out with the variations in the resistivity, variations in the density, temperature and pressure. Okay, so let us move on to the next question. At 10 degree Celsius, the value of density of a fixed mass of an ideal gas divided by its pressure is x. At 110 degree, the ratio is, so they want us to find out the ratio at 110 degree. So here density is rho is equal to mass by volume. Okay, so when rho by P is equal to x, which will become m by V into P. So x is equal to m by nRT, or xt is equal to a constant. Since mass is fixed, xt will become a constant. Both nr is a constant, so mass is also fixed. We can take it as xt is equal to constant, or x1 t1 is equal to x2 t2. x2 is equal to x1 t1 by t2. So here x1 value is x and t1 is 10 degree. So 10 degree means you are adding 273, so it will become 283 divided by t2 is 383. So you are adding 110 degree plus 273, so that will become 383. So the correct answer is option number 2, 283 by 383 x. Okay, so you're taking the density formula, mass by volume, and here as per the question they have given the density of a fixed mass of an ideal gas divided by its pressure is x. So rho by P is equal to x, so which is equal to m by V into P, and x is equal to m, because PV is equal to nRT. So PV is equal to nRT, you are substituting here nRT, and except T all the values are constant since the mass is also fixed. So xt will become constant, and x1 t1 is equal to x2 t2. So x2 you are going to find out, you know the value of x1 t1 and t2, you are going to substitute in it. That's all. Okay, so let us move on to the next question. A gas mixture consists of 2 moles of oxygen and 4 moles of argon at temperature T. Neglecting all vibration modes, the total internal energy of the system is. So the internal energy of the gas with F degrees of freedom is given by U is equal to F by 2 N RT. Now for oxygen, F oxygen is given as 5 by 2, and for argon it is 3 by 2. Okay, so the total energy U total is given by 5 by 2 to RT into 4 to 4 RT. So if you solve this, you will be getting it as 11 RT. So the total internal energy of the system is given by 11 RT. Okay, so why we are multiplying 2 and 4 is, here we have 2 moles of oxygen, and next thing is here you are having 4 moles of oxygen. So that's why I'm multiplying 2 and 4, and F for oxygen is 5 by 2, and for argon it is 3 by 2, so you are substituting it there. Okay, so let us move on to the next question. The amount of heat energy required to raise the temperature of 1 gram of helium at NTP from T1K to T2K is. So here they want us to find out the amount of heat energy requires the temperature of 1 gram of helium at NTP from T1 Kelvin, that is from one temperature to another temperature T2 Kelvin. So the amount of energy required is given by E is equal to F by 2 N RT, which is equal to F by 2 N K T2 minus T1. So E is equal to F by 2 N into NA KB into T2 minus T1. So where N is equal to N into NA. Okay, and KB is the Boltzmann constant. So E is equal to 3 by 2 N NA KB T2 minus T1, because F is equal to 3 for helium. Now N is equal to M by M, which is equal to 1 by 4. So E is equal to 3 by 2 into 1 by 4 KB T1. So this will become E is equal to 3 by 8 Na KB T2 minus T1. Okay, this is small. So the correct answer is option number 1, 3 by 8 Na KB into T2 minus T1. Okay, it's a very simple problem. Just you're going to make use of the formula and substitute. You'll be getting the answer as 3 by 8 Na Kb T2 minus T1. Okay, so let us move on to the next question. The value of mu is equal to Cp by Cv for hydrogen and helium, and another ideal diatomic gas X whose molecules are not rigid but have an additional vibrational mode are respectively equal to. So they want us to find out the ratio of Cp by Cv. So here diatomic gases have 5 degrees of freedom, neglecting the vibrational modes. For hydrogen you will be having mu1 is equal to 1 by 2 by f, which is equal to 1 by 2 by 5, 7 by 5. So monoatomic gases have 3 degrees of freedom. So for helium this will become mu2 is equal to 1 by 2 by f is equal to 1 by 2 by 3, which is equal to 5 by 3. Diatomic gases will be having 7 degrees of freedom. So considering the vibrational modes for X, mu3 will become 1 by 2 by f is equal to 1 by 2 by 7 is equal to 9 by 7. Okay, so mu1 comma mu2, mu3 will become 7 by 5, 5 by 3, 9 by 7. So the correct answer is option number 2, 7 by 5, 5 by 3 and 9 by 7. Okay, so let us now move on to the next question. The volume V of a monoatomic gas varies with its temperature T as shown in the graph. The ratio of work done by the gas to the heat absorbed by it when it undergoes a change from state A to state B is. So here the Vt graph is a straight line passing through the origin, hence V is directly proportional to T because it is varying linearly, or we can take it as P is a constant. So del Q will become NCP del T, and del U is equal to NCV del T. So del W is equal to del Q minus del U. So N Cp minus Cv del T. Del Q by del W is equal to NCP del T divided by N into Cp Cv into del T. So del T will get cancelled, N will get cancelled. So you will be getting it as Cp minus Cv. So or you can take this Cp common. So 1 by 1 minus Cv by Cp. So in the case of a monoatomic gas, you will be having Cv by Cp as 3 by 5. So what will happen here is del W by del Q is equal to 1 minus Cv by Cp. You are taking the inverse of that. So this will become 3 by 5 it will become 2 by 5. So the ratio of work done del W by the gas to the heat absorbed del Q is given by 2 by 5. So the correct answer is option number 1. Okay, so let us move on to the next question. 1 mole of an ideal monoatomic gas undergoes a process described by the equation PV cube equal to constant. The heat capacity of the gas during this process is, so here they are given PV cube is equal to a constant. This is a polytropic process with N is equal to 3. So the specific heat capacity C is equal to Cv plus R by 1 minus N, which is equal to R by mu minus 1 plus R by 1 minus N. Okay, so for monoatomic gas, mu is 5 by 3. So this will become R by 5 by 3 minus 1 plus R by 1 minus 3. So if you solve this, you will be getting C is equal to R, because 5 minus 3, it will become 2 by 3, and it will become 3R by 2, and here you will be having minus R by 2. So when you solve this, you will be getting the answer as C is equal to R. So the correct answer is option number 1. Okay, so let us move on to the next question. 4 kilograms of a gas occupies 22.4 liters at NTP. The specific heat capacity of the gas constant volume is 5 joules per Kelvin mole inverse. If the speed of sound in this gas at NTP is 952 meter per second, then the heat capacity at constant pressure is. So they want us to calculate the heat capacity at constant pressure, and they given the gas constant value as 8.3 joules per Kelvin per mole inverse. Okay, so here since 4 grams of gas occupies 22.4 liters as NTP, so the molecular mass of the gas is 4. So M value is 4 gram mole inverse. Okay, and as the speed of sound in the gas is given by P is equal to RT by M. So where mu is the omega is the ratio of two specific heats, and R is the universal gas constant, and T is the temperature of the gas. So omega is given by mv square by RT. Okay, here M is 4 gram moles per mole inverse. So M you can take it as 4 into 10 power minus 3 kilogram mole inverse, and V value they have given it as 952 meter per second. So here they have given the velocity sound speed of the sound, and R value they have given in the question as 8.3 joule Kelvin inverse mole inverse. So this one, and T value is 273 Kelvin at NTP. Okay, so you are going to substitute it in the formula. Mu is equal to 4 into 10 power minus 3 into 952 the whole square divided by 8.3 into 273. So if you solve this, you will be getting the value in the range of 1.6. So by definition, mu is equal to Cp by Cv, or Cp is equal to mu Cv. Okay, so here the Cv value they have given, the heat capacity at constant value as 5, and mu value you know it is 1.6. So you're going to just substitute here 1.6 into 5. So if you solve this, you'll be getting it as 8 joule Kelvin inverse mole inverse. So the correct answer is option number 3. So first thing what you are going to do is you are going to find out the mu value, which is given by mv square by rt, and they have given the values of mass, they have given the values of v volume, and they have given the values of gas constant r and the temperature. So you're going to substitute, and after substituting you are going to find out the heat capacity at constant pressure by making use of the equation mu is equal to Cp by Cv, and the value of heat capacity at constant volume is given by 5. You are going to substitute and you are going to find out the value of Cp. Okay, so let us move on to the next question. The ratio of the specific heats Cp by Cv is mu in terms of degrees of freedom n is given by. So here they have told us Cp minus Cv is equal to R. So Cp is equal to Cv plus R, which is equal to 1 by 2 Nr plus R. So this will become n by 2 plus 1 into R. So mu is equal to Cp Cv, which is equal to n by 2 plus 1 to Nr. So when it is going inside, it will become 1 by 1 plus 2 by n. So the correct answer is option number 3, 1 plus 2 by n. So on solving this. Okay, so you are taking Cp minus Cv is equal to R, and Cp is equal to Cv plus R, and Cv you know it is 1 by 2 Nr. So you're going to substitute that here and you're going to find out the Cp value, and the ratio of Cp and Cv is given in the terms of degrees of freedom n. So they want us to calculate the ratio of Cp by Cv in terms of degrees of freedom n. So it is 1 by 2 plus n, 2 by n. Okay, so let us move on to the next question. The molar specific heats of an ideal gas at a constant pressure and volume are denoted by Cp and Cv respectively. If R is the universal gas constant, then Cv is equal to. So here the difference between two molar specific heats is given by Cp minus Cv is equal to R, or Cp by Cv minus 1 is equal to R by Cv. That is, we are taking the Cv outside to the other side. So it will become Cp minus by Cv minus 1. So this one you know it is mu minus 1 is equal to R by Cv, or Cv will become R by mu minus 1. Okay, so the correct answer is option number 2. Option number 2. Okay, so this is mu minus 1, sorry, it is mu minus 1 in the option. So the correct answer is option number 2. So let us move on to the next question. If Cp and Cv denote the specific heats per unit mass of an ideal gas for molecular weight m, then they want us to find out which relationship satisfy here. So Cp is given by mCp and Cv is given by mCp. Okay, so Cp minus Cv is R, so mCp is B. Okay, mCv R by n. So Cp minus Cv is equal to R by m is the correct option. So option number 3 is the correct answer. Okay, so you're just taking Cp is equal to mCp and Cv is equal to mCv because it is specific heats per unit mass of an ideal gas of molecular weight m. So Cp minus Cv is equal to R, we know. You're going to substitute here mCp minus mCv is equal to R, or Cp minus Cv is equal to R by m. Okay, so let us move on to the next question. The mean free path for a gas molecule depends upon diameter d of the molecule as. So the mean free path is generally given by L is equal to 1 by root 2 n pi d square. Okay, so here if you see, L is inversely proportional to d square. So the correct answer is option number 2. So it's a very simple question based on the formula. So here they given the mean free path for a gas molecule depends on the diameter. They want us to find out how it is related with the diameter, and the mean free path is inversely proportional to the square of the diameter. So L is inversely proportional to, or L is inversely proportional to 1 by d square. So the mean free path is inversely proportional to the square of the diameter. So let us move on to the next question. The mean free path for a gas molecule depends upon diameter d of the molecule as. So here again lambda is equal to 1 by pi d square n root 2. So this will become 1 by 4 pi r square n root 2. Okay, so you're taking d is equal to 2r. So if you put like that, then it will become 4r square. So d square will become 4r square, and similarly here lambda is inversely proportional to the radius, square of the radius. So in the last question they asked, it depends upon the diameter d of the molecule. So here it is gas, the mean free path of gas molecule depends upon its radius. Okay, sorry, it's not diameter, it is radius of the molecule. So it is inversely proportional to r square. Okay, so the mean free path for a gas molecule is inversely proportional to the radius, the square of the radius. Okay, so the same formula in the last question they were asking is how it is related with the diameter, and this particular question they are asking is how it is related with the radius. So in both the cases it is inversely proportional to the square of the diameter, and it is inversely proportional to the square of the radius. So I think this video have been useful for you for recalling some of the problems which is based on the concept of kinetic theory of gases. And as we saw, we were given more importance to two particular topics. One is speed, pressure and kinetic energy of gases, and the next one is specific heat capacities of the gases, because majority of questions were coming from these two particular topics. And the next majority was given to kinetic theory of an ideal gas and gas laws. So I hope this video would have been helpful for you to understand some of the basic formulas which are being used to solve the kinetic theory of gases problems. So I wish you all a good luck for your examinations. Prepare well and practice all the problems by memorizing the formulas. If you see most of the problems, you will be applying the formulas directly and you can solve it within a fraction of seconds. Okay, so I wish you all good luck for your examination. All the best and thank you for watching this video.